In this video, we're going to be talking about ionic bonds. An ionic bond is a type of bond formed when one atom gives up electrons and another atom takes electrons. Typically, it's between a metal and a nonmetal, and there's a difference in electronegativity between the two atoms of greater than 1.8. We'll talk about these last two bullet points later on, but for now, we're just going to be focusing on this first part of it being a bond formed when one atom gives up electrons and another atom takes electrons. So here I have drawn 4 Bohr models of, we've got sodium, chlorine, magnesium, and oxygen. And we're going to be using those along with these Lewis dot structures here below to help us determine which of these atoms is going to be giving up electrons and which atom is going to be taking electrons to form a bond between the atoms. So let's first look at sodium chloride is a compound that many of us are familiar with. It's table salt, NaCl. And sodium chloride, as the name suggests, is a bond between sodium and chloride and chlorine. We'll talk about naming later on. But it's between sodium and chlorine. And let's look at sodium's Lewis dot structure, or its Bohr model, and chlorine's Lewis dot structure, or Bohr model, and think about what might be happening between these two things so that a bond is going to form. So sodium, as we recall, it has one valence electron. It's in the first column of the periodic table. Everything in the first column has one valence electron. Chlorine is in column 7. It therefore has 7 valence electrons. And recall that the Lewis dot structures is just a very simple way to reflect the number of valence electrons only. Lewis dot structures are very useful here because the valence electrons are really the only electrons that are going to play any role in a chemical reaction. So a chemical reaction between sodium and chloride, it's only going to involve these valence electrons, represented by the dots in the Lewis dot structure. So we said that the goal of any atom is to get to 8 valence electrons. That's the octet rule, and it makes every atom its goal in life. It's its absolute goal to get to 8 valence electrons. That's what's going to make it happy. Sodium right now is very unhappy because it has 1 valence electron. Chlorine also very unhappy. It has 7 valence electrons, but they are so close and they are determined to get to 8. But pause the video real quick and look at these 2 Lewis dot structures and think about what sodium and chloride might do for one another to help each other out so that they can both get to 8 valence electrons. And it might help to also look at the Bohr model so that you can, specifically for sodium, so that you can see how it's going to get to 8 valence electrons through help with chlorine. All right, after thinking about that, you might have figured out that sodium having 1 valence electron, the second outermost shell has 8. So to get to 8 valence electrons, the easiest thing for it to do is to lose this, the 1 electron it has in the valence shell, and then now, kaboom, it has 8 valence electrons. So if it just loses 1, that's how it can get to 8. Chlorine, on the other hand, it doesn't want to lose any because it would take a lot of energy for it to lose all 7 of these electrons. But instead, it's actually going to try to gain an electron since it's only 1 away. If it just gains 1, then it can get to 8. So if it adds an electron here, then now it has 8 valence electrons. So looking at, sodium and chlorine, they're going to look at one another and say, hey, we can help each other out. Hey, sodium, what if you give away this electron and I steal it from you? And now sodium is going to have 8 valence electrons, and chlorine has 8 valence electrons, and they formed a bond, sodium chloride, which for now we can represent it like this. Yeah, we'll just represent it like this for now. But it's a transfer of electrons an ionic bond is a transfer of electrons. So sodium is completely getting rid of that one electron, and chlorine is taking it and making it its own. So let's look at another example here. So we've got magnesium and oxygen. Well, now we've got magnesium has 2 valence electrons. It's in the second column, and oxygen has 6. It's in the 6th column. So what might they do for one another to get to 8 valence electrons? Pause the video and think about it using the Bohr models and or the Lewis dot structure to figure that out. All right, hopefully we thought about that. We might see here that magnesium has 2 valence electrons. It's a little bit harder to get rid of 2, and for oxygen it's a little bit harder to accept 2, but they're going to make it work. And magnesium is going to give an electron here, and then it's going to give its other electron here to oxygen. And then we're going to form a compound called magnesium oxide, MgO. And with what these compounds look like, we'll talk about that in another video, but let's just look at the compound that's formed. So NaCl is sodium chloride, MgO is magnesium oxide. We'll talk about the naming later, but for right now, we're just observing that we have a transfer of electrons. So the electrons, both of these electrons from magnesium are going to oxygen, and oxygen is gladly taking them. Okay, now what if it's not a perfect scenario where sodium has 1, chlorine is looking for 1? What if we had a bond here between, what about if we had between sodium and oxygen? What would happen here? Sodium and oxygen. It's not a perfect match, but to give you a hint, I'm going to draw multiple sodiums and multiple oxygens, and maybe we can, after seeing multiple of them drawn, we can figure out what to do from there. All right, pause the video, think about it. What might happen to where sodium could bind with oxygen? How can that occur? What needs to happen? Well, hopefully we had some time to think about that. And let's look. So oxygen is looking for 2 electrons. It is not going to be happy if it only gets 1. It does not want just 1, it wants 2. It needs to have 2. Sodium, it only has 1 valence electron to give. It is not interested in giving, if it gets rid of this 1 valence electron here, it is not interested whatsoever in getting rid of any of these electrons here. So sodium only has 1 electron to give, and oxygen has to receive 2 for it to be interested in any kind of transaction here of exchanging of electrons. So hopefully if we thought about it, maybe we came to the conclusion that what if sodium gave away an electron here, and then what if we just had another sodium and they kind of teamed up and both donated an electron? Then we can get a compound of sodium oxide to where we will have 2 sodiums and 1 oxygen. And we'll talk about how these compounds work later on, but it'll look like this, where we have Na2O, and the 2 is going to represent the number of sodiums. So there's 2 sodiums and 1 oxygen. When there's only 1 of something, we don't have to write the 1. In fact, we just typically don't write the 1. But Na2O would be sodium oxide because we have 2 sodiums donating their electron to form the bonds with the oxygen. So again, and we'll talk about this at a later date, but we represent in a subscript next to the element is the number of that element in the compound that's formed. So Na2O is sodium oxide. That's all we have for today on ionic bonds. Just a very general, basic video on the on what an ionic bond is, and we're just demonstrating today that it is a transfer of electrons. It's a complete transfer of electrons, and we'll talk about these other bullet points later on. But if you notice, sodium is a metal because it's on the left side of the periodic table. Same thing with magnesium, left side of the periodic table, it's a metal. And then oxygen and chlorine, both nonmetals. They're both on the right side of the periodic table. So we kind of start diving into this that second bullet point of it's between a metal and a nonmetal. It's pretty much always going to be between a metal and a nonmetal. Also, it's a difference in electronegativity of greater than 1.8. We'll show you an electronegativity charts later on where you'll see that we recall that electronegativity increases as we go up and to the right until we get to the noble gases, and those are crossed off. But so oxygen and chlorine both have very high electronegativity values. They are pulling electrons towards them. They want electrons. Whereas sodium and magnesium have very low electronegativity values, to where they don't have any attraction for electrons really. They want to get rid of them. So it works out perfectly when one atom is attracting the electrons and pulling them towards them, and the other one doesn't want them at all and has very low electronegativity values. So just kind of a preview on what we'll be covering later on. But yeah, what I wanted to accomplish today is that it's a complete transfer of electrons.